Hello, my name is Christopher Schuck, and I'm a current postdoctoral researcher at Drexel University. And today I'm going to talk about the synthesis of a new class of max phases and MXenes. MXenes are a class of two-dimensional transition metal carbides, nitrides, and carbonitrides that were discovered in 2011, so less than a decade ago, and they've been studied due to their exceptional properties, including a redox-capable surface, hydrophilicity, high mechanical strength, and even electrochromism. Due to these exceptional properties, MXenes were initially used in electrochemical energy storage, but this has since expanded to a wide variety of other fields, including as an additive for polymer, metal, and even ceramic composites, as an electromagnetic interference shielding coating for environmental remediation, in water desalination, in capacitive deionization, or even for anti-cancer treatments using photothermal tumor ablation. So, what exactly are MXenes and how are they made? Typically, MXenes are produced from top-down selective etching of a bulk layered ceramic max phase, but occasionally from non-max precursors as well. In max phases, the blue elements here represent an early transition metal, such as titanium, vanadium, niobium, or hafnium. X, the gray or black elements, represent carbon and or nitrogen, and the red elements are A group elements, so aluminum, silicon, or gallium. When you submerge these ceramic max phases in an etchant, such as hydrofluoric acid or a mixture of an inorganic fluoride salt, such as lithium fluoride and hydrochloric acid, or recently using molten salts or a alkali extraction method, you will selectively remove the A layer, so this red layer here, and you will exchange that A element with a surface termination, so oxygen, fluorine, chlorine, or OH. And this is what gives it its natural hydrophilicity. After this etching process, you're left with what's called a multi-layer MXene. So all of these two-dimensional sheets are held together by van der Waals forces. And to separate these sheets, you can use a variety of delamination techniques, such as using inorganic intercalants, such as lithium, using different solvents, such as DMSO, or using organic intercalants, such as tetramethylammonium hydroxide, or just by using mechanical sonication. And what you're left with after this delamination is a stable colloidal dispersion of few layer or single layer MXene flakes in water, or a variety of other solvents of your choice. Currently, over 150 different discrete max phases exist, and the full list of possible chemistries that occur in max phases is shown in this periodic table here. With these different max phases, you can actually incorporate multiple M elements, multiple A elements, or multiple X elements, or any combination thereof to create new solid solution max phases. Furthermore, with each different max phase structure, so M2AX, M3AX2, or M4AX3, or later as I'll show M5AX4, there's different structures that can occur. And this means there's different places where the M and X atoms can sit relative to A, or different orders where the M and X elements sit relative to each other. Within the molybdenum vanadium system, we initially saw a wide variety of different max phases that could occur. Max phases have the p63 MMC crystal structure, and in these phases specifically, the C lattice parameter is significantly larger than the A lattice parameter. Moreover, the C lattice parameter is very dependent on the number of transition metal layers, so the MX layers in max phases themselves. What this means is as we get thicker max phase structures, the 002 peak, which is characteristic of a C lattice parameter, gets larger and larger, so it shifts to the left in max phases. So if you look at the M2AX structure, this is the 002 peak for the M3AX2, the M4AX3, and when we did this synthesis, we actually saw an the 002 peak for the M5AX4 here, which is significantly farther to the left than any other published max phase. Now, moreover, what's interesting is we only saw this when we had the specific chemical composition of 4 molybdenum to 1 vanadium. Moreover, we saw something very interesting with this synthesis. If we didn't use vanadium oxide, we used V2O3 in our case. For the synthesis, just in small amounts, we wouldn't form the max phase at all. Instead, we formed bulk carbides, which wouldn't be useful for the study of MXenes. Now, what this means is there's some kind of simultaneous aluminothermal reduction reaction occurring during our high temperature annealing process, and this is something we're studying more in depth to understand why this is necessary. When we looked at this material using a scanning electron microscope, we saw a structure that was very typical of max phases, so it's highly anisotropic layered structure with some splitting. That's completely standard with max phases. However, when we zoomed in using a transmission electron microscope, we saw something a bit stranger. So I just want to point out from the selected area electron diffraction, it shows what looks to be a standard hexagonal p63 MMC structure, but looking at it very closely, you can see that it has this very unique herringbone-like twinned structure. So we've never seen this with the max phase before, where it occurs on one of the internal M sites. So this is a completely unique structure. And it looks like within each of these rows that it's a solid solution, so you have molybdenum and vanadium occurring in both. Now, after submerging this max phase in hydrofluoric acid for 8 days, we were able to successfully remove the aluminum layer. So you could see the 002 peak shifts to the left as we have intercalated water, and then we use tetramethyl ammonium hydroxide to delaminate it. So you can see that the color of the powder goes from this very normal gray to a black and then to a dull gray film after vacuum filtration. Before we completely switch to MXene, I want to point out one other interesting thing we saw in this max phase. In one of the particles we analyzed with TEM, we actually saw these much larger stacks of layers. So this one particle seemed to have layers between 5 up to 17 layers of transition metal. We don't know if this was a unique particle with this, or if this is indicative of higher ordered max phases that can occur. After etching, we again examined this material using an SEM. Instead of the close-packed layered structure that we saw with the max phase, we instead see that the layers are pulling apart in an accordion-like structure. This is very indicative of using high concentrations of HF to etch, and very indicative of what multi-layer MXene looks like. If you zoom in on any of these sheets, you will see that the A layers are completely removed, and the MXene sheets are just being held together by van der Waals forces between the sheets. Zooming in even further, you can see that this twinned herringbone-like structure is maintained in the MXene, and moreover, the surface terminations are above here. We delaminated the MXene using tetramethyl ammonium hydroxide, and this is an image of a single flake deposited on an alumina substrate. And we used AFM to examine the thickness of it. So this is thicker than we would expect from just the structure, and this is due to the adsorbed gases still on the surface. After producing the MXene, we wanted to see if its higher thickness and unique structure led to any enhanced properties, initially beginning with thermal stability. With MXenes, what you typically see is you will see a release of the adsorbed water that's intercalated between the layers, followed by degradation and release of the delaminate used. What we saw is this occurred well below 500 degrees for this MXene. However, this MXene, so this two-dimensional material, was stable up until about 800 degrees Celsius, which is higher than any other MXene studied to date. Once we saw that this occurred, we produced two separate samples. One film that we annealed at 150 degrees to release all of the water, and one film produced after annealing at 500 degrees to degrade and release all of the intercalant. Typically, what you will see here is a large decrease in the electrical conductivity when you have an organic intercalant remaining on the surface as it changes its electron density. What we saw here is we saw that the conductivity went from about 250 Siemens per centimeter up to about 830 after this process. However, most MXenes will experience a 1 or even 2 order of magnitude change in conductivity after this. What this means is this MXene due to its thickness, has a higher protection against the organic intercalant changing its electron density. So its internal electronic state is not changing as significantly due to changes on its surface. Moreover, what we see is a positive magnetoresistance occurring with this MXene. We're not exactly sure why this has a positive magnetoresistance, but this has been observed a few times with molybdenum-containing MXenes already, and it's something we're investigating further. We were also interested in investigating the optical properties of MXenes. Typically, MXenes are very unique in their color, that they have characteristic absorption peaks in the visible region. So you can have different colored films. So Ti2C would be green, Ti3C2 is a purple, NB2C is gold. And each different MXene composition generally has a different color in its colloid and in its film. With this MXene, initially I was a bit disappointed. We saw this dull gray color, which didn't seem too interesting. And when we looked at the optical properties, even up to 250 nanometers, we saw really no characteristic absorption peaks. It seemed that this MXene really transmitted all light. This is in contrast to most other MXenes, which have characteristic absorptions between the UV and near IR regions, depending on the composition structure. This is very unique, and it allows us to make devices for applications that no other MXene or really many materials can do. This is very valuable for optoelectronics because you can make spray-on transparent antennas. If you spray this material onto a perovskite on top and under, you can make electron transport layers that do not significantly change the light reaching the perovskite. If you were to remove ITO, you can make flexible electronics if you would spray it onto plastics or other flexible substrates. So by not absorbing really any light from UV to near IR, this opens up a new pathway to produce a wide variety of optoelectronic devices that no other MXene can do. After we discovered the first M5AX4 and the M5X4 MXene, a question quickly arose. Is this a unique structure, or is it a member of a larger family of MAX and MXene? We reached out to our computational collaborators at UPenn, and they did a high throughput study to understand what other M elements would be appropriate to make these M5X4 MXenes. And it looks like many max phases and MXenes could exist with a wide variety of chemistries. It seems that there's many different stable phases that can occur, and it's just a application space that hasn't been truly investigated yet. It may be the case that some of these require unique synthesis approaches, so using different oxides like we did for an aluminothermic reduction, or it could be that they just require very specific conditions to exist. Our computational group also investigated the stability of if this is an ordered structure, so if you have the molybdenum and vanadium separated versus having them be random and solid solution oriented. And they found that it seems that the solid solution systems have the lowest energy, so they're the most likely to be possible. So one thing that we need to do is we need to more broadly investigate the chemistry of max phases to see if we can produce other phases of the M5X4 structure. To date, over 30 discrete MXenes have already been discovered. This study added this entirely new column to the MXene family. As we investigate more max phases and consequently MXenes, we discover new properties that have not existed before that we didn't know could be possible. So each new addition to the family provides us an increased level of understanding of the chemistry and physics of MXenes and 2D materials as a whole. And the M5AX4 and M5X4 family offers a new route for synthesis of MXenes with extreme properties, and it may be possible to even increase this thickness further to N=5 or above. It's something we will have to investigate.
Finally, I would like to thank everyone who made this possible. Specifically, I would like to point out Grayson, who is an undergraduate student who spearheaded this effort. And I would like to thank our funding agencies, Drexel CRF for characterization, and our collaborators, Vivek Shenoy and Eric Stock, who performed the TEM and computational analyses. And finally, I will take any questions you may have.